Hello. Let's see what happened. Huh. Now I even wonder, maybe we didn't have link earlier. It's odd to think that it just disappeared. Okay, so maybe we'll start the class in and we have an one. Okay. Hmm? Okay, I'll see you on Thursday, or you can stay here too, whatever you like.
It's fine, I'll go. Thank you.
Okay.
Bye.
Bye. All right, so maybe, yeah, I think we have we usually have this much people to begin, and by the end of the lab, we lose like quite a bit of a people. So I believe it's safe to start. What do you say? Okay, thank you. So I want to go over electric field inside the conductor. And this is part of the midterm. Electric field inside conductor. Maybe I'm going to go into the notes. Okay. So let's see. What's conductor? What does conductor have and the insulator don't have? What's unique to the conductor? Right. Everybody agree with Feynman's comment? Conductor have, oh, have free electrons. So any conductors have electrons that can freely move. How they move when you have electric force and they move. So what it means is that you have let's say electric field, right? Here is the electric field lines. Then these E minus, they're going to feel force against it. If it's E minus, you're going to have a force and they'll move along the electric field line. If it's negative, it goes opposite direction. If it's positive, it goes into, if it's a positive, you have electric field lines. If it's a positive, it goes along. Right? If it's free to move, it's going to move along the electric field. So whenever you have an electric field, they're going to move. But electrostatic, for electrostatic, that means that it's stationary. It's static. So net force has to be zero. Agree? So when if the conductor have an electric field, these free electrons, they'll move. But they cannot keep moving for static. So they'll move in a way to make sure that net force becomes zero. Move to make sure inside conductor, because they can move. That means that for the net force to be zero, you have to have, you cannot have any electric field inside. If you have any electric field inside conductor, these free electrons, they're going to move. So at the end, they'll locate in a way to make sure that electric field is zero. Charge arrange themselves. Again, the charge, electric charge, arrange so that the conductor equals zero. So all the charges, if you have any charges, let's say, if the conductor can be charged, it doesn't mean that they can't have any electric charge. They can be having electric charge. But what happens is that all these charges, they'll move at the surface. Arrange already wrote that. They're gonna be at the surface. So let's see. If I have a big metallic ball, there's this big metallic ball, right? And this one has the plus Q, let's say. Then all the charges are going to be at the surface. They're going to move and then straight themselves in a way that electric field inside is zero. Inside is zero. That means that all the electric field line has to be coming outside. E has to be coming outside. There's no electric field lines inside the conductor. That's why they go to the surface. Does that make sense? Thank you. So they go to the surface and the only electric field lines can be coming out from to the outside. And also another thing is that they're coming out perpendicular to the surface, these electric field lines. Imagine if you have any tangential component along the surface, that means that charges can still move. It can move. And then we don't have any motion. Any tangential component causes charge motion. So electric field line, they only move in a way that electric field line only have a perpendicular to the surface. There's no tangential component. So you can see if it's a spherical, electric field line comes out radially outward. When you have for example, when you have a shape like this, little pointy, like a square shape charge, then all the charge tends to come more in pointy spot. So they come out like this. Very few on the flat area, but more, it tends to be more on the pointiness. Another one that you could have like this kind of a shape, let's say, then a lot of charges is going to be accumulated. There'll be more here, less here. So again, electric field lines, it's going to be a lot coming out like this, all perpendicular to the surface, and then a little bit less here, but definitely more from this way. So if you have a pointiness, and then if you have a the charged metal has a pointiness, that's where the charge likes to be, at the pointy area, because they have to come out radially outward. Again, what's the electric field inside the conductor? Thank you. You gotta say it, guys. Electric field inside conductor is always say it. Thank you. It's always, thank you. Right. Right. Electric field inside the conductor is always zero. Always zero. So we use this metal to shield from electricity. For example, airplane flies and then often it flies through the rainy clouds. it's actually, it's not uncommon that airplane get hit by a lightning. Airplane struck by lightning once every 1,000 flight hours, which means that a few times, one or twice in a year, you have the airplane gets struck by a lightning. And then I myself, when I was in airplane, got struck by lightning. You just hear a boom sound. Sometimes you might see a spark if you're near the window. But we don't, airplane doesn't fall down, right? By getting struck by lightning. What's the airplane made of? Right? Metal is stops, shields. Shields. Very good. Metal acts like very good. So metal is a conductor. Conductor have free electrons. Free electrons shields the electric field. So electric field inside the airplane, electric field is always zero. Inside the airplane, because the airplane is typically made of a metal. These days, the new airplane is actually made of graphene, which is not, it's like a carbon, but they still make those metal grid, and then you have to surround it and then complete it perfectly to shield, so that all the electronic device is being shielded by the conductor. So here is the video that how often you see that airplane is getting struck. It's pretty common. I don't, only the first part is, they'll show it. You see? So typically when the airplanes get struck by lightning, it tends to start from the pointy end. So it may, the lightning comes into the wing, the tip of the wing, and then runs through only the surface and then comes out from the tail. Or it gets struck by the tail and it comes out from the wing. So the pointiness to the pointiness. That's where it enters and comes out, and then only runs on the surface. And then when you're inside the airplane, you don't feel it. You hear the sound and things, but you don't have a problem with the electric field inside the airplane. Everybody see it? Like here, where is it? You see it? It gets struck by a lightning. So you can find out a lot of videos that has the airplane actually being struck by lightning, and you're safe inside the conductor as long as the conductor is surrounding the entire airplane. Let me see. So therefore, when I ask, oh, I'm gonna stop the sharing. I'm gonna ask you this question. There is a lightning outside. And you're driving the car, but your car ran out of gas and you stop. Where do you want to be to avoid getting hit by a lightning? And there is a little house, you see? but the house doesn't seem like it has any lightning rods. And there's a tall tree. Or stay inside the car. Which would be the best place to avoid getting hit by a lightning? And you're going to be able to, you got to explain why. This little house that don't have a lightning rods is made of a wood. About the half of the glass. Okay, good, good. Hey, what's the, so the house is made of wood, no lightning rods. Tree, tall tree is there. You can cover yourself from the rain for both cases or stay inside the car. We don't have too many people attending the class, so you guys should participate. Pick your answer. Mine as well. You're here. Mine as well. Just participate. I'm going to be closing. Closing. Here. So it's very good. Again, the house is made of wood, trees, tree, but car is made of yep. Car is made of metal. So the metal car inside the metal conductor, its electric field is 0. If you have a lightning rod, then the pointiness of the lightning rod is you're going to have a charge accumulated. So it's going to go in here, especially if it's tall, pointing up, then this little pointiness is going to attract the electric lightning because you can have a charge that's accumulated at the pointy end. So that comes in and then it goes out to the ground. And the ground acts like an infinite bath for the charge to be. So it just goes in and to the ground. That's how the lightning rod is made. That's why the lightning rod is made of metal. And then you just on purposely attract it to the lightning rod and then escape out. Yeah. So yeah, of course you want to have a make sure the gas tank is not connected to the, outside metal and things like that. And a lot of people say stay inside the car because tire acts like an insulator. And it is true when the rain, the rainwater is a conductor. So it gets wet and you have you can have a high current that passing through on wet surface. And then if you're insulated away from that, it's safer too. If you're staying on the ground, it's really bad because then you have a lightning happen somewhere else and then a current can pass through your body if you're wet too. And if you're touching the ground, that's wet. So it's better to be insulated from the ground. That's one thing. But also, if you're inside the car, that's inside the metal, electric field is 0. So you can shield yourself from the external electric field. If you're inside the metal, so there's also another, they have, I made a demonstration and look, I look so proud of this. Have you been to the science museum that you see those like a sparkle of like electricity coming out? And then you see it's in the metal grid. It's surrounded in the metal grid that you're outside, you're okay. Tesla coil, yeah. When you see the Tesla coils, it's always, you have always a metallic grid. So here is my proud video. I play, let me see, I play KCRW on the radio. Let's see. KCRW, Santa Monica radio station. And then I have something I have here. What I have here is the metallic grid. It's also known as a Faraday cage. Here. So here I have a radio. It's turning to KCRW 89.9, Santa Monica College radio station. What else I also have is this is the metal grid. Metal grid, and this is a conductor, metal. I'm turning on the radio. No more touch. Let's put this radio in the grid. See how it does. You see how the music goes away? I'm going to open it. Close it. Right? I'm so proud. Okay, I'm going to turn it down. It's because that inside the metal conductor, electric field is always 0. And this is called Faraday cage. Yeah, so inside the conductor, electric field is 0. There's a free electrons in the middle that moves in a way that makes sure that there is no electric field inside. Fun? All right. Any questions? So sometimes when you have a, nice stereo system, or when I was doing some sensitive experiment, I want to shield it from outside noises, electric field noises. Then you surround your nice stereo or electric equipment with even enough with aluminum foil. Just cover up. Then you're gonna get cleaner signal. You don't have as much disturbance. So try that if you need it. Shield it with a metal. Questions? After here is the electric field midterm 3 that I'm going to open up soon. Just let me make sure about the time and things. Anybody have a questions?
How long is the test going to be open for? Or till when?
Yeah, until Wednesday midnight for sure. Means Wednesday. So you're going to have one full day tomorrow, and then today's afternoon.
It sounds good. Thank you.
Yeah. I'm worried about the time.
And how many questions is it?
I have so far I have a 3 plus one more. Another one is just only to upload file. So 3 plus 1 question about the file. And then those 3 ones, it depends on the section. I have a lot of writing though. Maybe writing, I may change that writing into a multiple choice because I just really, people can copy down from the website, And then if you are doing truthfully, you need time to write it too. So it's hard. Maybe I should make more multiple choice. I don't know. This has to go with the trust, and then I'm gonna I'm gonna do my best to be careful with wording and also check your work. But as long as you're doing truthfully, it should be okay. But time is the concern. I'm not going to be there to be able to extend your time. So. So chapter 22, any questions from homework? Do you have it today to be the due date, right? 52, 60. So let's see, 52. Sharing. Tumbling. Why do clothes often cling together after tumbling in a clothes dryer? Is it the wrong one? doing something else? I'm looking at homework. Yes, yes. Is this the wrong question? Oh, we look at the 14. Yes, I'll do the 14. And then why don't I do 52 first? Because I already wrote down. Thank you. Yes, I'll definitely do number 14 and 22. And then right now, let me do the 52. Sounds good. Thank you. I didn't see that. Chapter 22. Ah, it's different. Okay, okay. I'm looking at you're right. It's different. So I got a new version, new edition of a book. I gotta be careful. All right. Number 52. This is the correct one. Why is dust attracted to UVD wiped with a dry cloth? This is it. So this is electrostatic. Those wipes, the Swiffer and things, you see those Swiffer, even the duster, the feather dust stuff you have. It looks fancy, like wiping off the surface like this, right? You see that there's like a little fiber that's coming out. It's just so what you're doing is to, by friction, you cause electrostatic, and then you attract all the dust particles. So you use electrostatic force to, you're not just physically taking off the dust. You're actually attracting using an electrostatic force to those small dust and things. So it's not just only the physical motion to get rid of the dust. Interesting, right? We use the electrostatic force for number 52. Any questions on number 52? Otherwise, I'm going to move to requested one, that number 14. So semiconductor, you don't need to worry too much. Number 14 asks, how does a semiconductor differ from a conductor or an insulator? You don't need to worry too much about semiconductor. Semiconductor has both the property of being an insulator and a conductor. The electrical property can be altered by like external force, like you apply a light, or it could be thermal, or it could be by impurities, adding impurities. It can be changed from being an insulator to non-conductor. So that's the property of semiconductor. Semiconductor can be one or the other, depends on the condition. But other than that, I want you to know, make sure you know about the conductor means free electrons, insulators means no free electrons. Therefore, if you don't have a free electrons, how why still get attracted? If it's a neutral, like you don't have a free electrons, what kind of a mechanism can you have to attract the neutral insulator? What kind of a mechanism do you use to attract a neutral conductor? I want you to be able to explain those two. All right. $14. Am I answering your question, Odin? Number 14. Good, good, good. And number 22. Thank you for this. What is an electric dipole? So good. Number 22, ask. This is good though. Remember, I asked you to draw electric field of a two charged particle that's opposite side. Do you remember that? So this is actually pretty good because I want you to be able to draw some of these electric field of all this electric configuration. Let's see. So let's see. I want you to be able to draw, if you have a 1 point charge, electric field lines of the positive will look like this. 1, 2, 3, 4, 5, 6, 7, 8, right? Then remember, if you have a 2Q, you should have arms that's twice more in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, enough, 11, 12, 13, 14, 15, 16. So 16 arms, right? And remember, I asked you to draw, what does this plus Q? And if you have a two charge, same charge, but separated by distance D, this is called dipole. Two same charge oppositely. Two same charge oppositely charged particles separated by some distance. So it looks plus Q and minus Q, something like that. How does the electric field line look like? Remember? You could be here when the test charge is here, it's gonna be repelled from plus Q, gonna go towards minus Q. So it's gonna look something like this. Is that right? Thank you. Any atoms with the distance, right? I can talk about water molecules, yes. Let's talk about that after we do the electric field lines of electric dipole. And then if I put the test charge here, it's gonna come out from plus Q, wanna go inside the minus Q, radially come out, radially in, come out, in. It should be top and bottom should be symmetrical. So these are the electric field lines. Of dipole. So it's not, it doesn't have to be molecule or atom, or it does not matter as long as it's just oppositely charged. So if this one has 2 positive 2, this one has to have a minus 2 coulomb, or lost 2 electrons, it has to be gained the 2 electrons. It could be even inside this one molecule that has the dipole. Yes, Earth. So we gotta see the Earth do have a magnetic dipole. Magnetic dipole. It's a magnetic field. So you have a north and south. But this is electric dipole. Electric, it calls from electricity, electric charge. Electromagnetic is a little bit different from electric field. Is the electric field is only from the electric charge. Magnetic field is from the magnetic source. And then once we get, if we don't get into magnetic field, but magnetic field is actually coming from motion of electric charge. So it's a little bit different. Electromagnetic field is made of both electric field and a magnetic field. But electric field is just coming from electric charge. This charge can be stationary, it can be moving. Whenever you have an electric charge, you have an electric field. Magnetic field is not the case. Magnetic field, you have to have a moving electric charge. But electromagnetic field is you need to have both the electric field and a magnetic field. So it's different. Similar, but different. So the Earth dipole moment that we talk about, it looks like a very, this electric lines, field lines, looks very similar to what we see with the magnetic dipoles, right? Magnets, you have a north and south, and you play with those sands that has some iron bits in it, and then it makes this kind of a shape. It's going to be the exact same shape, but this case, it's not about north and south pole. This is about north seeking pole and south seeking pole. This is a plus and minus charge, electric charge, which is not the same as a magnetic source. So this is electric field. Meaning that electric dipole is not the same as magnetic dipole. So let's see. Very good. You know, water. Water, I mentioned that's conductor, right? Water is H2O. So you have a 1 oxygen and then you have 2 hydrogen. So it's made of 2 hydrogen and 1 oxygen. These molecules, it forms a molecule by sharing electrons. So O oxygen has 2 minus, and then the hydrogen shares the positive and a positive. Hydrogen shares the electrons, and the oxygen here also shares 2 hydrogen and 1 oxygen shares the electrons. And it's going to be positive on the hydrogen side and the 2 minus on the oxygen side. But how they form this molecule is always formed in like a Mickey Mouse shape. So you see that inside the molecule, it's naturally positive on one side and naturally negative on the other side. So water molecule is neutral. It's electrically neutral, but naturally, because of the shape of the molecule, how the atoms are formed, making up a H2O, you have a slightly positive on one side and slightly negative on the other side. And then this is called dipole. 2 plus and 2 minus. So water have an electric dipole moment. That's why that it's conductor. So you don't need to have a free electrons, but you have a one side to be slightly positive, the other side to be negative. So water molecule, water is a fluid, so it can move. So all this dipole moment can move around once you have an electric field established. It goes along the electric field. Even though it doesn't have a free electrons, it has the dipole moment, electric dipole moment. I want to talk so much, but we have to move on. Any more questions? Number 8. Good. What is meant by the charge quantized? Number 8. Sorry. It means that charge is quantized. Doesn't move. Good. Charge is quantized means that how can an object be charged? It's the transfer of electrons. And these electrons, each electrons have a negative 1.6 times 10 to the minus 19 coulomb. You can't have a 1/2 the electron, or you cannot have a 3.2 electrons. Electrons has to come in integer number. You don't have a half U. So each time you get charged, it has to be the integer of electrons, or integer of negative 1.6 times 10 to the minus 19 coulomb. So that's what it means by quantize. Means that you don't change the charge gradually. You only change the charge. Amount of charge can be changed from 1 electrons or 2 electrons or 3 electrons. It doesn't go from 1 to 1.8 and things. So that's what it means by quantized. Anybody else have a question on this? Number 60, how can you charge an object negatively with only the help of positively charged object? How do you do that? No response? Telling. Which is called, very good, which is called what? What kind of a mechanism is that? Mhm. This, can you charge in an object, this object, number 20, sorry, number 60. Very good. Number 60, right? This neutral object. Can you charge the insulator or conductor? Does it matter what kind of object, electrical property does it have? Good. Can you charge the neutral object to be negative with the positive charge object if it's an insulator? Or conductor? Why so? Why so? I love that. Thank you so much for the response, though. How about other people? If you just possibly, I'm sorry. Hold on, I'm gonna cut down now. Oh yeah? Why so? Why so? Hold on. Sorry. Let me see. So why insulator? Yes, and then not the conductor. Stop sharing. So you went. I need to put this back again. resisted. So good. Let's see, what is that? So when I say insulator and conductor, what is the difference between an insulator and conductor? What's the definition of a conductor? What does the conductive material have? And then what does the insulator material have or not have? What is the difference? Insulator. Whenever you hear word insulator and conductor, you need to write this definition. Always go back to the definition. So whenever you hear neutral, loose. Good. So whenever you hear neutral means that no same number. Insulator and a conductor, the difference is conductor have free electrons. Conductor has free electrons. Insulator do not have a free electrons. Electron cannot flow freely in the insulator. Conductor have electrons that can flow freely inside. Okay, so go back and make sure that you just always just conductor equals free electrons. Insulator means no free electrons. All right, then how can you charge an object? And so does this work with, it just says object, but it won't work if it's an insulator. It only works with the conductor. Why? So this is like a conductive metallic can, metal. It's initially, it only works with the conductor. And you want to use only, what was it? Positively charged object. So you have a positively charged object. Mm. So positively charged or negatively charged means that either imbalance number of electrons to the protons, right? It's the electrons that's change, the electron is the one that transfers, not the protons. So if you lose electrons, then you get positively charged. If you gain electrons, then you get, the object gets negatively charged. So it's the transfer of electrons. To be positively charged part object, you lose deficiency of electrons. You have an excess electrons, then you have a negatively charged object. So this positively charged object here, this one has the deficiency of electrons. Yeah, but this one has a deficiency of electrons. So how do you charge this object? Why does it matter if it's an insulator or conductor? It looks like only Odin and sometimes Fatima is participating. Others? I mean, no, I love you. That I like that you participating and yeah. But hey, others too. You guys also have to participate. It's really good that Odin has been positively participating, and sometimes Fatima. Hey, so how? Tell me, why does it matter if it's a conductor or insulator? If you have a positively charged object and if you have a conductive material, how to charge this conductive material negatively? Or how can you ever charge the material? Remember, first you can charge by friction. Right. And then if it's a conductor, you use, like Justin says, induction. Right. Thank you. So conductor, induce electric charge. Nice. So induction. So another thing, so you need to put that in. Insulator means no free electrons. Conductor means free electrons. And if you have a free electrons, you can induce the electric charge, which means that since it has the free electrons, when you bring the positively charged object nearby, I'm glad that, well, I don't know why he doesn't close the door. Nearby, then it induces the free charge inside, free electrons inside the conductor. Minus one is going to be attracted to the positive side, and then the plus one is going to be repelled onto the other side. Remember that? But this induction, this is induction, but this is still electrically neutral. So how can we negatively charge this object? You have to keep this positively charged object nearby, keep it there, while inducing a charge, you have to touch the other side. And your hands are conductor, so the positively charged one is going to go through you while still keeping a negative on the other side. And then if you move away, there's only negative that's left. So it's going to be negatively charged. Right, negative charge attract the positive charge. So, or positive attracts the negative. So it goes on the other side. So you have to touch the opposite side then the positive one goes down on through you. And the negative one is still going to be attracted by the positively charged rod nearby. And then you remove your finger and you remove the positively charged object. Then you can charge the metal. Can you do this with the insulator? No. Does this work with the insulator? Good. Good, good, good. Only friction. Insulator, you can induce the charge, but charge won't flow through your finger. So you can induce the charge separation, but you cannot charge. Very good. Can we charge this metal positively? With the same setting. So now I have a positively. So if so, how? Positively charged rod and then neutral can metal. How can I charge positively? Can we or not? Same situation. It can be. Oh. Okay, thank you, thank you. If it's no, explain why. If yes, how? This is helpful for me too. I may change the exam. Right, but this is still a metal. It's still a metal. Thank you. But in this case, I want to charge positively. We charge negatively by using induction. Now I want to charge this metal, which has a free electrons, positively. Can I do that? Just using the same setting. I have a metal, positively charged object and a neutral metal object. Can I charge positively? Maybe yes. Good. How? If it's no, why? Protects it. Via conduction, Conduction. What do you mean by conduction? Very good. Conduction, what does it mean by conduction? Right. Touching. Lose electrons more easily. It transfers. Metal has a free electrons. So the electric charge can move freely inside the metal. It can move freely inside the electrons. So when you touch it, touch. Then, oh, these electrons are the positive charge inside. There is more space. The conductor means more space. It moves. It can move. So this positive will move into the middle. And then you move away. This is going to be positively charged. Does this make sense? So make sure when you explain, use define physical quantities clearly. That means they can move. All right. Let me stop the recording. I'm going to cut off the recording. So hopefully it's going to get uploaded quickly. Let's see. So the other group can also watch this. Do you have any more questions? Let me see. It'll be a very good idea to make sure you do the part 2 before you do the midterm exam. I'm going to stop sharing for now. And then I wonder, if I make a second meeting, because I want to make sure that it gets uploaded quickly. I think the shorter it is, it's better. Do you have any more questions from the chapter 22 homework? 106. Okay, let's do 106. So yes, if you're cold outdoors in a thunderstorm, why shouldn't you stand under a tree? Can you think of a reason why you should not stand with your legs far apart? So let me see, 106. Very good. If you are cold outdoors in a thunderstorm, and can you think of and I'm going to share the screen again. So this one we just kind of did. That a rain, the water is a conductor. So the tree, the tall tree is when it's wet, right? If it's wet, it's a conductive material all over. So if it's conductive material, when it's wet, the pointiness gets the most charge going to be accumulated on the very end of the top of the tree, right? So that's where the lightning tends to hit. Is everybody okay with that idea? It comes here. So when it comes here, it's going to go through here. You definitely, then you don't want to be close to the tree. You're going to get hit by lightning. So this part is okay. All right, so this part is okay. So why you shouldn't be standing, so you don't want to be under the tree. Why you don't want to be standing legs apart? To stand legs apart, right? That means that, so when the lightning happens, this is going to be the source, sort of a big Q. Right? So electric potential is the highest, let's say here at that moment, and it's going to be with the same distance. There is going to be the voltage like this. Is everybody okay with that? So electric voltage is going to be equipotential line, let's say, is going to be here and then here, radially outwards. That means that from here to here, you're going to have a voltage drop. Or you can think that there's going to be an electric field line that's coming out like this, E. Force. So if you have a charge, that charge can go, likes to go like this or like this. Does that make sense? It can pass through you because you're standing along the electric field lines. So force, it creates the force. So if you have a legs apart, that means you create the voltage drop. Whenever we're going to do this in the next chapter, you have a voltage drop or change in voltage, you have current flowing. Electrons pass through because you have a force. Change in electric field pushes. If you're standing, but if you're miraculously standing along the same potential line, then that particular special case, if you just happens to spread on the same potential line, then you may not have electric current passing through. That it won't have a charge passing through. But that's very, very unique case. Most of the time, you stand in a way that you have a different electric field. Then you're going to have an electric field that's pushing through. The force is going to be passing through. Does that make sense? That's why you don't want to spread your legs apart or even laying. Ooh. Laying flat on the ground is like so many electrons pass through along the electric field lines, right? Again, you miraculously find a way to be only on the equipotential line, then you might not have any electric force. But most of the time, you're going to have some kind of a difference in electric field, or I would say difference in voltage that you're going to have charges passing through. If you have two locations. Am I answering your question? Very good, very good. Everybody else, that's you understand? So the key words here to explain it is that different two locations means two different voltage. So change in voltage means electric force. So that charges. So these are the keywords, right? Two locations, two different voltage, changing voltage, force, charges run through your body. So again, make sure you use the correct physical quantities, right? Analyze the case using the correct physical quantities. Define it correctly. When you say shield, I want you to be clear what it means by shield. You gotta, don't write just protect. What do you mean by protection? You need to explain in physics using the physics variables, physics quantities, physical laws. I can't give you points if you don't use the correct term. So that those vocabularies that you should know is really important. Thank you for the question. Really, really appreciate. right. More questions from the homework? All right, then I'm gonna stop sharing and I wanna find a way to, so I think what I'm gonna do is to make another link for the, we're gonna have a short break and let me cut. Okay, I'm gonna get back, take a screenshot. Thank you everybody for the participation. Really helps, really helps. So let me see. I'm gonna end this meeting, make a new link. So I can upload, hopefully this is gonna be uploaded on the website quickly that Thursday people can also watch it before taking test today. Sounds good. And then I will make a new link so we can see you guys at the new link to go over other chapters if you like. All right. So let's see, it's, thank you. It's 10:50, 11 o'clock, 11:05, 11. Let's see you. I will make a, we'll make a new link. Confer now. Starting at 11 a.m. Okay. See you there. Thank you so much, guys. So I'm going to end this meeting. Okay, I'm ending. I made a new link. All right, see you there. Or if you have any questions, let me know. Okay, I'm ending.